Good morning, everyone. Today I'm very happy to introduce Jeongwan Haah, who spoke yesterday at the SNS. Today he's giving a talk here at the School of Math. He's an expert in an intersection of physics, math, and computer science. I don't know if you agree to that. And he worked a lot on quantum error correction. He's the author of the Haah codes. And today he's talking about something coming from functional analysis to complexity and very cross-disciplinary. So I encourage people to ask questions. You have enough time for interruptions, so take it really in.
Thank you so much for the introduction. Here. I know I allotted for 2 hours slot, but I'm not sure if I will fill it out. Let's keep it interactive. So the goal here is to prove that. There is an algebra generated by this diagram. It's an operator written on the lattice. I will get to this, some important properties of this, but this is a really concrete thing. I'll just show you here. I'm happy to send you the mathematical script here. So the goal is to analyze that algebra, and the theorem we are getting to is that algebra is not isomorphic to the tensor product algebra. Okay, we'll get to we'll understand what it means. So, just to give you a little bit of context for the computer science audience, let me start with the very trivial looking situation. So, think about a Boolean cube. And I consider a distribution of this Boolean. Say, I assign two probability mass for just two bit strings, and 0 for all the other. This is one distribution, and another distribution is to another, similar looking distribution of this. Now you can ask a question, which has a lot of a similarity to what I'm going to talk about. I want to transform this bit string, this distribution, to that distribution using some reversible circuit set. And since this is all about physical context, I only allow like a one-dimensional connectivity. So namely, I can only operate on, say, nearest neighbor triple of bits at a time. And then I ask, how many gates do I need from here to there? It's not a function, it's just a transformational distribution, but I ask about complexity of transformation. So the answer is linear in the depth is linear in the number of bits. How do you argue that? How do you argue that? Well, number of gates is also linear, but depth is linear too. How do you argue about that? I make a cut. And then consider the mutual information between the two. In this case, there's no correlation between this party and that party. In this case, there is a correlation between the left and the right. And that is true for every possible cut. But if you have a reversible gate, and you transform this to left to right, any reversible gate acting on the one party would not change the correlation. The mutual information will stay the same. So there must be some correlation between the two. And in fact, if you just consider correlation between here and here, that correlation is also not non-zero here, but 0 here. And that correlation function can only change whenever you have some connected array of gates that will connect the two. Otherwise, you wouldn't develop the correlation. That's the argument for the lower bound on the depth.
So make it a little bit more formal. I mean, what is the... So we assume I had a circuit which was not on, which had sublinear depth. What will be exactly your contradiction? You have a progress measure, right? You have a progress measure. This progress measure is the correlation.
Yes.
You're saying you start at 0, you are in the 1 maybe. And if the depth is sublinear, it jumps by more than 1 over n at some point, and this contradicts something.
Right.
So we are just a bit more precise.
So you think about the fast lightcone in this case. The observable that you see will be located at the end of the block. And since we have a local circuit, there will be a domain of influence for that bit. And the domain of influence is contained in this lightcone. The existence of lightcone is coming from an assumption that I'm using the local gates only. So if you have a sublinear depth, actually depth is, say, well, n over 10, then the past lightcone would not overlap and there would not be any correlation. Does that make you happy?
Really more, but not completely, but so on.
Okay. So a similar story happens when you consider the encoding circuit of code. So now the time goes to the right. So you start with some you think about the distribution over the all unencoded code words. This is just the k bits of distribution. And you want to map this onto the distribution of a classical code where the individual bits are now mapped onto some code word. And suppose this has some large distance, large minimal distance. The minimum weight of a non-zero code vector has to be some large, like maybe linear. And any transformation circuit using local gates in this one-dimensional geometry will have to take a linear depth at least to create such distribution by the same argument.
Again, sorry, what's the source on the left-hand side? This is code words, or this is just Boolean strings, the left?
This is just a Boolean string. I just tilted this by
All Boolean strings, or
all Boolean strings on k bits, and the n minus k bits are now set to 0. And that distribution is now mapped onto the uniform distribution over the code.
the same distribution, but we want to map it to a linear code.
Yes, yes. So in encoding circuit. Actually.
So just to clarify, usually when you encode all the messages, not just
Yeah, it's all the messages.
Yeah, all the messages.
It's all the messages, but if you want a reversible circuit, you might as well add some zeros at the side. Yeah. But there are k bits encoded in n bits and the distance.
What is D here? Omega D?
And
Oh, just and the distance, but it's really n.
The distance, okay.
I'm just cartooning it at this moment. Okay.
The bound is linear, independent of the code, if I understand.
Given that the code has distance linear. Okay. Now let's think about the same problem, but with the quantum codes. So quantum code for this hour is, for this moment, it's just a linear subspace of a many-qubit Hilbert space. And that is defined by the stabilizer condition. So, That's my code space.
Or can you read it out? So subspace, it just says the linear subspace of this.
Yeah.
And what you decide?
It consists of vectors in this tensor space, such that it takes the eigenvalue 1 for operator P that is called stabilizes that code space. And the P ranges over some abelian group of Pauli strings. Pauli strings, I mean, like something like that.
Can you explain more?
Sorry?
What are E, X, and Z? Can you explain more?
Okay. So this is a shorthand notation for 2x2 matrices.
All is determined by the abelian group, right?
Yeah. And of course, for this to be non-zero, this group should not contain minus identity.
Just to say, so you tensor any one of these x0, or maybe also x times z,
Yeah.
n times.
Mhm.
That's the group of all Pauli matrices, and you're taking some
Subgroup.
subgroup of them.
Yeah.
That's your subgroup, and then I guess that's all the p's come from that subgroup.
Yeah.
And then you're looking at all the states psi that are stabilized by this subgroup. P of psi equals psi, and that's your code space.
Yes. So that definition. Okay. So there is analogous notion of the minimal distance in the classical code in the quantum regime, which is you think about the So quantum code distance is defined analogously to the, following the spirit that, if you, in the classical setting, one interpretation of the minimal distance is that if you corrupt that many bits, then there's a chance that you are transforming some non-trivial, you are mapping a code word to another. So similarly, I want to think about the best case of the quantum setting where I have to access to the qubits in such a way that I implement some non-trivial transformation in this subspace. So this is the condition for my Pauli operator to preserve the space. So it acts within the space, it maps the space to itself. And this condition ensures that this induces some non-identity transformation.
So could you explain more about what is this Q pad?
Q what?
Q pad.
Notation of the bracket.
What's a commutator?
Commutator.
Weight of Q is the number of non-identity.
Right. So yeah. So you count the number of non-identity components, and that's the weight.
That's what I get for the definition. So you want the minimum weight of Q where the commutator is 0 and the other Q is not in the.
Yeah, not in the group.
Not in the algebra, presumably.
It's equivalent. Because I
Is
only
Q a Pauli string?
yes yeah.
Basically, one would worry about any unitary,
Yes.
not just a Pauli string.
Yes. But for the sake of simplicity, we only focus on the Pauli strings, which has good reason that the algebra that preserves this pi is anyway a span of generated by these Paulis. Okay, so what's the analogous question to this? The analogous question is you consider an arbitrary vector living inside some k qubits worth of space, and then you initialize everything else in zero state, and then you run some encoding unitary circuit, and you end up in some state in my code. And I ask the question, it's no more a distribution anymore, because quantum state and distribution are very anonymous. Many people will, some years ago, some people would say quantum computer could be faster because it has access to the exponential things and so on. But that reasoning is completely wrong, because the probability distribution over bit string is also parameterized exponential in many numbers. Anyway, so we ask analogous question for the complexity of this encoding circuit. And by the same lightcone argument, if I insist on the geometry locality here, then the encoding circuit must be deep as the code distance in this sense, because it has to map some operator that acts non-trivially here, which could be a single qubit operator, to an operator that acts on at least the number of qubits. So that's the lightcone-based argument for a lower bound of the complexity.
Sorry, the pi is a set of states, or you are assuming it's uniform superposition of the codes?
Here, pi is just a subspace, but in this case, it doesn't really matter, because I only ask about the operator that acts on that space.
But your input is, like before the encoding circuit, it's a state, and
yes,
the output is also a state.
Yes, but the encoding circuit should work for every state.
What is psi?
Oh, just a notation for our arbitrary state here that is supported on the k qubits.
And what's the condition for the output?
For the output, for every vector in this subspace, you must land within this space.
But you don't assume they are distinct?
Oh, if it is unitary, then they're automatically distinct.
Oh, okay.
Okay.
So what is the bound of the complexity?
The same. The depth of the encoding circuit must be at least the codistance. A linear codistance.
You replace correlation by entanglement, entropy, or what? The argument to prove it. What do you will explain?
Yeah, the argument is same in spirit, but maybe slightly different in the detail. So pick an operator here that acts non-trivially on this subspace. That will be a single qubit operator. Such an operator passes through this encoding circuit. It will be conjugated by this encoding circuit and produce some operator that induces non-trivial transformation in this code space. But by definition of the code distance, any non-trivial transformation on the code space must be induced by the weight d or larger operator. And if your circuit is too small, then there's no time for the circuit to produce such a high weight.
Sorry, what are you assuming about geometry of the gates? Is it just K local, or are you also assuming it's spatially local?
Spatially local.
Likely to be weaker.
Yeah. Yeah. Otherwise, you would the lower bound will go down to a lofty. So basically, this has been the only argument behind the scene whenever you encounter some lower bound that has some geometrical locality built in. Spiritually, there's always a lightcone argument that you must have generated like this long range correlation, or the operator has to grow like this big. Therefore, you could not have achieved otherwise if the circuit was too shallow. Now, let's okay. Let me phrase this question in terms of a little bit differently. Let's consider just a phrase differently. The content is exactly the same. Let's consider the algebra acting on this space. It'll be 2 to the k by 2 to the k matrix. Then this encoding circuit is now giving an isomorphism from that algebra to another algebra that acts on this co-space, which is also 2 to the k by 2 to the k matrix embedded in some way.
Embedded in 2 to the n by 2 to the
2 to the n. Yeah. So we have a non-trivial inclusion of the algebra of a smaller dimension into a larger one. And so this encoding circuit unitary conjugation is inducing an isomorphism between this algebra and that algebra. And we are giving a lower bound on the isomorphism. Okay, so the algebra I want to talk about is living on an infinite lattice. So let's move on. You can now forget about that. So the algebra of interest, the ambient algebra of interest, which I will denote it by this, is so we know how to construct a 2 by 2 matrix algebra. And we can tensor product 2 algebras together. And if you give me a sequence of those, then there's a way to define the infinite tensor product. How do we do that? It's just a formal procedure, just as we construct real numbers out of rationals. So we think about the inclusions. So I ranges for some set, which could be infinite, and for every finite set in that S, you associate just a finite tensor product, and then call this as an A of F. Then we have a directed system induced by the inclusions of this matrix, inclusions of this index set. So if we have such an inclusions, sequence of inclusions, then we can think about the associated algebra, the finite tensor product. And whenever the inclusion is proper, we insert just identity tensor factor. This is a very a different situation than a vector space. In a vector space, when you tensor product many vector spaces, there's no canonical choice for the auxiliary vector space. But for the algebra, there is the one. So that canonical choice allows us to talk about this easily. The index inclusion, there is associated algebra inclusion, and this diagram commutes. And then
F1 and F2 are of the same dimension.
No.
So why is this going back and forth? What is this?
No.
Oh, okay.
I'm sorry, there's a hoot there. Yeah. So, and then you appeal to the direct limit, which is exactly the same as thinking about the sequences in place of some truly infinite thing. It's our proxy to talk about the infinite tensor product. One more, yes.
Couldn't you just say that your infinite algebra is generated by the operators that act on just one qubit?
I could say that. I mean, this is the underlying formalism behind that sentence. If you are familiar with that, then you don't have to do this. Okay, so since I want to talk about the geometric locality, I also endow a metric on this S. So in my case, S is going to be Z squared, the integral grid in the 2 dimensions, and there is a notion of metric. So I can talk about some operator acting here is now far from the operator there. So we have a notion of support at the distance between. So So then in that context of geometrical locality, the important morphisms between algebras has to be local. And this is the definition for it being local. And I call it bounded spread. So you give me an arbitrary element in that infinite tensor product of algebras in the plane. Then I consider some map from its, some endomorphism. And then the condition for the bounded spreadness is that it will be mapped to here, but the support of the image must be contained in the support of X with a slight enlargement allowed. So, like, if you have some local unitary gate that is acting on my system of qubits, then the maximum possible support increase from that gate will be limited by the support of the gate itself. And any finite composition of those will have this property with a slightly worsening parameter L. But there exists L that applies uniformly across my lattice, and I demand this L to be uniform for it to be about this spread.
Sorry, I think I can't see can you read that?
Support of the image is contained in the small neighborhood of the support of the domain.
Neighborhood in Z squared or?
Yeah,
Yes.
Okay.
Yeah. In that metric space.
the operator is confined in some region, then the image is confined in a slightly dilated region by editing.
Okay.
So now the goal is to show that you remember the diagram exactly, right?
Therefore,
Let me call that algebra generated by those operators by Curly. It is a subalgebra contained in this. There are actually more than one qubit per site. In this discussion, I literally assign a 2x2 matrix per every point. But let's increase that number a little bit. For this particular example, actually there are 4.
4x4.
Yeah.
Some
uniformly bounded number. Yeah, completely unimportant number. So, yeah. So here comes one theorem that N is not P is the local dimension.
The number of values of these qubits or whatever. Yeah.
For any P, as long as it's uniformly bounded, my algebra that you remember from my screen is not bounded spread isomorphic to anything.
So this is something that's not true if you just do Z. Suppose you did it on a one-dimensional lattice.
Great question. Yes, it is not true. Well, yeah. I mean, the theorem is very, very important that you have 2 here. My specific algebra lives in 2 dimension, which is translation invariant generated. So I only showed you like 4 diagrams, and the algebra generators are those operators and the translates of those. You multiply them, you sum them over, and that's my algebra. And because of the translation invariance, you could have defined it on a cylinder, long cylinder of some finite circumference. In that case, this theorem is not true. In that compactified along one dimensionally reduced algebra is isomorphic to by this spread isomorphism to the matrix algebra in one dimension.
I still didn't get the P.
P is some arbitrary number. So, like 2 here. This is completely unimportant. I could have had a 3, 4.
It's a number, it's not qubits you're asking on, it's on a quantum particle that has P values.
So, and the 2 to the 4 is the same with P to the 4, or?
Doesn't have to be. Oh, okay. So, slightly more stronger. So even if you stabilize the algebra by tensoring in some, this I call trivial algebra. Even if you tensor in some trivial algebra, still it is not isomorphic to anything trivial.
The triviality is that it works in each component separately, as opposed to.
No. The triviality is my technical term. By trivial algebra that looks like this. So more formally, there exists a local dimensional assignment with which we take an infinite tensor product, and such an algebra I call it trivial.
It's not obvious that the dimension of A is asymptotically the same as the dimension of any such thing.
Dimension of this.
Yes. You have a locally generated algebra.
Yes.
But it's not obvious that asymptotically of a large lattice, its dimension is asymptotic to that of matrices D2P.
Great question.
So
Right.
If it isn't, then your statement would hold even without the band spread condition.
Right. But in this case, dimension of A is precisely half of 2. Sorry.
Square.
Yeah, square root of 2 to the 4, so it's going to be 2 to the 2. So why is this example any interesting? Because this is, as far as I know, the first example of such, in the sense that, in the following sense.
I mean, the statement you made about the one-dimensional system.
Yeah.
So there everything is any algebra that I guess the translation invariant that you could decide will be included in a central product.
That is the
trivial will be square
Yeah.
bounded in your sense.
Yes, that is.
Is this easy to see, or this is?
No, it's not easy to see. Actually, it's one of the components that I will sketch. I have spent 30 minutes so far, but yeah, we'll see.
Yeah, we make sure you talk 2 hours.
Okay. So, in which sense this is interesting? There is a criteria for us to talk about the local algebras, and it goes under the name of net of algebras. This is a very abstract notion that closely mimics the construction here. So instead of assigning an algebra that is a tensor product associated with every finite set of points, I assign some algebra. Okay. So for every subset of my lattice, some subset of my metric space, it is associated with some algebra. Well, let's make it finite dimensional to be concrete. And then it satisfies this compatibility condition. And you can now talk about the inductive limit, and we can talk about the infinite lattice and so on. But to impose the locality, there's extra conditions, which is the following. If you give me a disjoint union of two separate regions, U and V, then it has to be generated individually. I require, in addition to this assignment, I require that you give me two separate balls. Well, it doesn't have to be a ball, some separate sufficiently separated two regions, then algebra assignment to that separate set has to be just generated by those of the here and those. That's my first condition. The second condition is you consider the inclusion of the smaller subset into the full thing, and then you take a commutant. So you collect a set of elements here that commutes with every element there. That's my prime. Then this prime has to be contained in so let me decipher this notation. This is my U. Minus L is L distance inside. So theoretically, you take a complement of U, take a L neighborhood, and take a complement again. So you take a smaller set, and you look at the outside of this interior. That's what this is about. And there's this is a subset of the bipolar lattice, so there is associated algebra. And any operator that commutes with everything on U must be contained in the outside of U. That's the spirit. And I allow for a small parameter to give me some room to
And this outside has to be defined by this limiting process, which does not use this property.
Right. Yeah. I mean, so by this limiting process, for every set, I do have an algebra, regardless if it is finite or infinite.
Okay, for compatibility and for defining of the limit, you don't need these two properties. You impose them afterwards.
Yep.
So isn't this the other way around? Any operator outside U has to commute with operator inside U, but you can also have, as your algebra is generated by commuting operators, then the commutant of U also includes entire U.
No, I do not allow for that sharp commutant. I'm sorry. I do not demand that sharp commutant relation. Anything commutes with U is contained in the outside of U. That's the word. Now, why is this notion interesting? Because this notion of derivative algebra is invariant on their bounded spread isomorphisms. You increase the parameter L a little bit. That's it.
And L is fixed. It doesn't depend upon U.
The formal statement is that this system is a derivative algebra if there exists an L such that this holds uniformly across every region. Yeah. And if you apply a bounded spread isomorphism, then you may have to increase your L a little bit according to the spread appearing in the bounded spread isomorphism here. But as long as it is uniformly bounded across all lattice, I'm fine. So this property captures. It's behind the board, but it captures the lightcone argument. The fact that the statement that this property is invariant on the bounded spread isomorphism is capturing all the lightcone argument before. So you look at the given algebra. So I wanted to compare. I wanted to talk about the isomorphism between this algebra and that algebra, and you think about, do they satisfy this property? And for all those previous examples, it is satisfied in one example, but not the other. And that was the source of the complexity lower bound. Now, the very algebra that you all remember on my screen, that satisfies this. So in that sense, the previous lightcone-based argument is not helping me to prove this theorem. So in that sense, this example is interesting.
So if you forget about locality, as a C-star algebra, is A just isomorphic to just a UHF algebra like MATC?
I was going to that. So let's not worry about the infinity too much. So so there is something called the Wedderburn-Arkin theorem, which has nothing to do with the locality, but so if you give me let me state the theorem. I used A. So think about an algebra contained in my matrix of n by n matrix. This is finite, nothing complicated here. And suppose I consider the subalgebra of that is closed under taking transpose conjugate. That's called the star algebra. And this theorem tells us the structure of this. Oh, by the way, I demand that the multiplicative identity here is mapped to the 1 here. So the inclusion is unitary. Then there exists a unitary in my n by n matrices such that you conjugating this my algebra that is already contained in my matrix algebra has this form. So there are blocks. So U is basically diagonalizing my algebra. And the theorem says there exists a block diagonal decomposition of my this algebra. Every element in this conjugated B has this form. Some blocks are repeated. Some blocks appear alone. And then it goes down all the way down to the bottom.
Well, you have to say something more because it can be just one block.
It can be yeah. So the theorem is there exists, some
there is a universal set of these diagonal, the sizes of these.
The size of this and the number of multiplicity that depends on B.
Yeah.
But that's all information B got.
No, they are irreducible. This is the point.
Sorry?
The A's are irreducible.
A's are irreducible.
You want to say
Yeah.
that A is
You have to
full
say-
matrix.
Yes. Yeah.
Yeah.
In particular, if B does not have central element, in other words, if the element of B that commutes with everything in B is always a scalar multiple of identity, then you only have a single block repeated some number of times.
No, if it's repeated some number of times, the commutant is more than good.
No, it is still that because I insist on the repetition. They have to be synchronized. And if you're an element of center of B, then it has to be expressed in this way.
The center, sorry.
Yes.
You didn't say the commutant.
Oh, no,
It's a
center.
scalar.
Central. So I can compactify the notation like this. Tensor notation. So one corollary is that any central subalgebra, star subalgebra of my matrix algebra, the full matrix algebra, the rank of that, my algebra must divide the total rank. Now, why am I mentioning this? So my algebra, I didn't tell you the properties of my algebra. My algebra is central. It does not have any central element other than the scalar. So if you define on a torus, on a compact setting, then it's finite dimensional. So this theorem applies. So then my A is going to be of this form. It turns out that the commutants of my algebra in my laptop, if you take a commutant within this full opera algebra, then it itself is isomorphic to itself. It's a special property of my example.
The commutant is just all commutators of elements of A and the general.
Right.
You commute it with any other algebra element, and you get back element in it.
Yes. So if you consider a torus, again compact thing, running into the finite setting, then this tells us that the dimension of A is exactly the square root of the full dimension. And it's central, so it must of this form. So if you just give me a half number of qubits in my system, then by this Wedderburn theorem, it is isomorphic to A. But it does not tell you about the complexity because the unitary arising from this theorem has no knowledge about locality. So rely on this, I know my algebra is isomorphic to some qubit algebra. And then now, of course, the question is how to say something about using bounded algebra as well.
Sorry, I'm confused about something. So say that it's that this algebra A is isomorphic to something that seems much smaller.
Yeah.
Can't I just keep nesting that until it becomes?
Oh, it's not smaller. It's not smaller. It's exactly half.
Yeah, but why can't I?
But the smaller looking thing isn't similar.
Oh.
Okay.
Here's an example. The algebra generated by these two matrices on a two qubit system is isomorphic to the algebra of all operators on one qubit.
Right. Yes.
The dimension is exactly the square root.
Right. Okay.
Okay, so
Can you say what central means?
sorry.
The me central. Can you say it again? Like
A is central.
yeah.
Center is zero. Center is trivial. Yeah, now, okay, so let me write down the sketch of the proof.
So you are just going to leave these two properties of A. This will your COM holds for any A.
Oh no. Actually, it's got a lot of detail actually. But whose property I will lay down. There are words that I didn't even define yet. So stay for a few minutes for me. I will get into every word here. So this is the rough sketch of the argument. Let me so okay, which one would you like to hear first? There's a word QCA, there is a word invertible subalgebra, there's a word fermionic, there's a yeah. Okay.
Yeah, what is that last, and number 3, what does that last sentence say? That last equation say?
Here.
What is that?
Oh, fermionic QCA in dimension 2 is trivial.
So I'm confused about the fact that like statements 1 and 2 don't reply to A at all. Like A only shows up.
Right. A only shows up in 3. Good point. Yeah, very good point. So let's, okay. Since I have defined bounded spread homomorphism, the QCA is easy to define. It's an acronym exactly standing for bounded spread automorphism. It's an acronym of quantum cellular automata for historical reasons, but there's no reason for you to think about it as a cellular automata. It's literally bounded spread automorphism. Okay, so that takes care of the QCA part. What does F mean? F. So we'd like to think of not only just the matrix algebra, but we want to think about the graded algebra. What's a graded algebra? Let me reserve the notation A for my specific one and B be some other algebra. B is called graded if it is a direct sum as a vector space of the 2 components. This is called even component and that's called odd component. With the multiplication rule that B so if you give me an element from here, and if you give me another element here, so I stands for the subscript, and the B and B prime, they are some general element. If you multiply 2 elements from the graded components, then you end up in this component. So this times this is here, this times that is there, this times this is here. And the most important operation using the graded algebra is when you tensor product 2. So B tensor C, I'm going to define a graded tensor product. Tensor algebra, how do you construct it? You give me 2 algebras, you tensor product. What does that do? As a vector space, algebra is a vector space over the underlying scalar. As a vector space, it is equal to just the usual tensor product of the 2 vector spaces. Addition follows the usual distributive law. There's no complication around that. But you can make a choice for the multiplication. So in the usual algebra that is ungraded, when you define a multiplication of 2 elements, you literally do this. That's my rule. And then you have to show that this forms an algebra obeying the distributed law and associativity, and you can do that. In the graded algebra, you twist it. IJ, AL, IJ, AL. But it comes with the extra sign that depends on the grading of this and that. That's my twist. Why does it form an algebra? You can do your homework.
And JK is the multiplication.
Multiplication.
0, 1.
Multiplication.
And 0, 1.
Yeah, 0, 1. Yeah. And this is a graded algebra, and this is the mathematical model to talk about the Fermions in lattices. And under this multiplication rule, you follow this inductive limit to talk about the fermions on the infinite lattice. And so on. How does it look like? Okay, so let's understand akin to the Wedderburn-Artin theorem in the usual matrix algebra. I want to understand what how it behaves. I want to understand the representation of the fermionic algebra. Fermionic algebra is synonymous to the gradient, the Z2 gradient algebra. In the finite dimensional, when the algebra is finite dimensional, there are extra assumptions, but I will ignore about that. Due to the semi-primitivity to avoid certain things. But in the finite dimensional case, there are the trivial, one example is something like this. I forgot to tell you one important thing. Graded algebra, graded algebra comes with an involution that maps you insert a minus sign in front of the odd element. It's just extra data that you endow to a graded algebra. This is called a fermion parity. You may have zero-dimensional odd elements, which is the case for the usual matrix algebra. So our usual discussion of matrix algebra is a special case of Z2 gradient, except that the odd part is just 0. So that's an example. Another example is, I will denote it like this. It is a matrix algebra, but with the assignment of odd elements in the off diagonals. So here I'm drawing a figure where A is equal to 2 and B is equal to 1. There you write down a 3x3 matrix and declare that any element that has a non-zero elements here and here, they are even. Just declare that. And any element whose non-zero entries are only on the off diagonal, you declare that odd. Why is it graded? Well, first, it is direct sum, vector space. And then the involution is implemented by the conjugation by this matrix. If you multiply that matrix, sandwich the element, then these blocks will pick a minus sign. That amounts to the grading involution. And there is another type of algebra, which I call denoted by this. And this has a matrix representation of this form. So you synchronize the diagonal blocks and synchronize the off-diagonal blocks and insist that this is 2n by 2n matrix. And declare that these elements are odd, these elements are even. And that is a gradient algebra.
Is there a shorthand physics way of talking about what you just said?
What?
Is there a physics way of saying what you just said?
Oh, I don't think there's an analog for this example. This is, oh, okay. Yeah, this is just so, and this example is a 1 random mode attached to a function. So as an exercise, you can show this is a graded tensor product defined there. This is a trivially graded algebra. This is a two-dimensional algebra with the one-dimensional odd element and the one-dimensional even element. And your tensor product, then you do get that. So just these are the finite dimensional examples of the graded algebra. Now, what's FQCA? FQCA is you do this. It's a QCA, so it's a bounded spread isomorphism, but the underlying algebra is now graded. That's it. So every local site, you assign a finite dimensional one of these. Anything's fine. You assign those, and then you think about the bounded spread automorphism of that algebra. That's my FQCA. Okay.
I'm going to ask the same question again. Is there a physics way to say that, maybe in terms of like circuit language?
Circuit language.
Is it like circuit language like quantum circuits or
the FQCA?
FQCA, yeah.
So you choose a homogeneous unitary in the okay. So let's bring it down to the finite dimensional study. Yeah. Say we have I don't know, maybe 4 Majorana modes. This is F minus 1 to the fourth gradient tensor power. In this algebra, well, what's an example of? Let's forget about the bounded spreadness, but let's think about the one automorphism. One automorphism is a conjugation by gamma 1. That is an automorphism. In fact, whenever you bring a homogeneous element and that it happens to be unitary, then you can conjugate, and then you achieve an automorphism. Of course, whenever you see an algebraic object with a lot of structures, whenever I say morphism, it should preserve all that property. In other words, when I talk about the isomorphism, homomorphism, whatever, morphism must commute with this grading evolution. Even element to the even, odd element to the odd. And at the same time, it should preserve all the multiplication and addition. So FQCA is a graded morphism, the graded structure that happens to act on the Fermionic algebra. That's FQCA with the extra conditional bounded spreads. Okay, so now let's talk about the invertible subalgebra. The definition is the following. You give me an algebra and I want to say that this is invertible. A subalgebra of my some either fermionic or bosonic is okay. I say it's invertible if you consider this the commutant of the original algebra within the full mother algebra, and you take an abstract tensor product. then by the condition that it was a commutant, oh, by the way, in the graded case, you should take care of the parity component, but let me skip that. Because I choose the commutants of this multiplication map, like B prime tensor B map onto B prime times B, it is an algebra homomorphism. The non-trivial fact is that so I should be mapping this equality that comes from the definition of my tensor algebra to be preserved under this morphism. And this will be mapped onto B prime B under this map. This will be mapped onto C prime C. This will be mapped onto B prime C prime B C. Well, they're not the same, but since I take the first component to be the commutant, you can commute this too. And you see the same things. So this is an algebra homomorphism. The graded case you should plug in some appropriate signs, but it's not difficult. So it's a homomorphism. So I have a algebra homomorphism from the abstract tensor product into my mother algebra. And I demand by invertibility that this has a bounded spread inverse.
Did you say that B prime is a bounded spread of algebra? So it has the same axiom as B?
No. The bounded spread is an adjective for the morphism.
No, I'm sorry. You had some conditions in your setup that B should satisfy. You want B prime to satisfy the same conditions. Quasi-locality and so on.
Oh, I do not impose.
You do not?
However, it follows.
I see.
So in this sense, I named it invertible. Now you ask, what does it have anything to do with QCA? And here comes the connection. So I'm going to construct a map from a given element of a QCA. I will construct a invertible subalgebra. And given element of invertible subalgebra, I will construct a QCA. So the forward map first. QCA is by definition a bounded spread automorphism of the underlying operator algebra. But underlying operator algebra has a tensor structure. And tensor structure, I can think about the slices of algebra. So every point is associated with some local operators. But I could easily think about a subalgebra generated by only those red points. No problem, it's a subalgebra. And then I map, so let the QCA be denoted by alpha. This red subalgebra that is supported in the half semi-infinite plane or space is mapped by alpha to something. It's bounded spread isomorphism, so automorphism. So this operator should be mapped onto something fuzzy but stays local there. Deep in this side will be mapped also on deep in that side. Well, I don't consider any operator there, so I don't care about that. Now, this is an automorphism. So in particular, it has an inverse. And it turns out that inverse is also bounded spread isomorphism. I didn't tell you, but it is true. And if you consider an operator in the codomain that is deep in the bulk, then its pre-image, the inverse of that red dot, will sit in somewhere here. So every operator deep in the bulk side will have pre-image sitting in the domain side. In particular, the image of this semi-infinite space algebra, it contains the full algebra supported on the red yellow. And then it turns out that such subalgebra is always a tensor factor. I'm not going to prove that for you, but yeah. Any of the subalgebra of this form is a tensor factor if it is contained in it. So
tensor factor of the image.
Sorry?
The tensor factor of the image.
Yeah, factor of the image. So alpha of the image of the half-space algebra contains this. You go sufficiently deep in the bulk, and the pre-image must be residing in the original domain, so it is a tensor factor. And turns out this is equal to it's a tensor factor.
Is half space here is important?
What is that?
Half space here important?
Half space is important, yes.
And you do not get this if you truncate it to like a constant size region.
Then, well, you could do that, but the argument and the formula becomes somewhat ugly. Well, in that sense, you may say half infinite space is not important. And now here comes a non-trivial claim that this missing piece is an invertible subalgebra. What do I mean? That this unknown piece, where does it live? First, where does it belong? It belongs to here. It's bounded spread. And it commutes with every element deep in the bulk. So it may not have any support there. The only place where this blue piece could be is in this window, where the size is about like 2 times the spread parameter. So we are effectively, we started with a D-dimensional QCA on automorphism of bounded spread, and now produced an algebra living at the boundary of that, D minus 1 dimension.
The same argument would work in particular in dimension 1.
Yes.
And then you get just the constant.
Yes.
Then.
Yeah. So you get some finite dimensional object. Okay, I'll skip the proof why this is invertible. But just to give you a hint why, how do you get this bounded spread inverse? You use the tensor structure in the domain side. So you bring some arbitrary element here, map it back by alpha inverse. It'll be straddling between the boundary of my region, and using that tensor structure, you decompose, push it forward, then you realize the decomposition that is required by the okay, now the converse map. So you give me a data of invertible subalgebra. Essentially, you are giving me the data of a bounded spread inverse, and I want to construct an automorphism of an operator algebra that lives in the one dimension higher. So this is always in the D-1, and this is only in D. How do I do that? Here comes the very convenient feature of the lattice. Lattice, any dimensional thing, is a collection of points. In particular, the D-dimensional lattice is a collection of D-1 dimensional sheets. So each piece is now D-1 dimensional integer lattice, and the whole thing is D-dimensional integer lattice. And what information should I specify to define a map? Well, you only have to define it for a generator. This is it's going to be an algebra homomorphism. So, and what's the generator for this D-dimensional lattice? Well, some single-sided operator in one of the sheets. And at that point, there's only one data I could use, the inverse of this bounded spread. So you give me an element there, you apply this bounded spread inverse, it will give me some decomposition. Where A resides in my given invertible subalgebra, and B resides in the commutant of my invertible subalgebra. And my definition of the QCA is now to map this B piece to the next layer. So the upper script is the sheet index, the K is the observation index. And by QCA alpha, I map it to So you map one of the components to the next layer. You're basically pushing, you slice your algebra here according to this map, and then push the one slice off to the next layer. And that's my morphism. And due to the commutativity and relations and so on, you can verify that this is indeed an algebra homomorphism, and you can construct the inverse and so on, and you do get a QCA.
Sorry, can you remind me what's the distinction between A and B here?
A is an element of my given invertible subalgebra, and B belongs to the commutant. Now the theorem is that maybe I should call it a lemma because it is all geared towards the final proof. You consider the equivalence relation of the invertible subalgebra by the bounded spread isomorphisms up to stabilization. So you give me two invertible subalgebras, and then you wonder if they are equivalent. And by definition, if they are equivalent, if you could find some other trivial algebra of the tensor form such that you can find the bounded isomorphism between the two. In that case, I declare that two invertible subalgebras are isomorphic. Under that equivalence relation with the tensor product operation, this forms a group, which I call a Brouwer group, which properly extends the traditional classical notion of Brouwer group for a given field when you consider the central simple algebras over that. Now I'm going to introduce another equivalence relation on the QCA. And that is given by the blending equivalence. So I say QCA alpha, you find on give me a two QCAs, say alpha and beta, and I want to say they are equivalent. If there exists a third one, such that gamma is equal to alpha on left half space, and gamma is equal to beta when restricted to right half space. So there's some crossover. So this is after all a function, and the data of this function is contained in the images of the single site operators. Everything else is derived from the being a algebra homomorphism. So, and I require that data to agree with that of gamma on the left half space and agree with beta on the right half space. So that's my equivalence relation. Then,
so why can't you define gamma to be you are given alpha and beta?
Yes.
So they are defined by their actions on the site.
Yeah.
Okay. So can't you define gamma to be the action of alpha on the left half plane? I may not be an algebra, may not be an algebra automorphic.
Right. Well,
that's what the most natural thing with what's a problem. I do it.
Right. That's one thing. Another thing is I require gamma to be bounded spread as well. Alpha and beta are bounded spread. There are some parameters, and the gamma bounded spreadness should be enforced. In that case, I say there is a blending. Yes.
So alpha and beta are not translation invariant.
No.
They're just bounded spread.
Alpha and beta is defined on infinite space.
Yes.
Once you try to merge it, then you include the boundary. Is that okay? Like just isn't alpha and beta all defined only in the infinite space?
The absence of the boundary is the key in this equivalence relation. The very condition that you could introduce a boundary between alpha and beta is an equivalence relation that I'm defining. You may not be able to, in which case I should declare that they are different.
Is a nice example of non-trivial alpha and beta.
Quantum circuits. Quantum circuits. So perhaps most important and boring example of a bounded spread isomorphism is given by the geometrically local quantum circuit of some constant depth. So you have some gates drawn in the sorry,
local one-dimensional local.
Yep. So yeah, this is one dimension, and all the d minus one dimensional are compressed in this. And then I can blend this alpha to identity by this. For every local operator deep in the inside, we'll only see this many gates. So the action is not changed. On the right-hand side, you don't see anything, so it's identity. So quantum circuit always blends into identity.
Something like a translation to the left, for example, does it blend?
No. So the important lemma for this step one is that QCA up to blend, and I'm going to ignore shifts. This is a group under the usual composition. It's equal to dimension D is equal to the Brouwer group of invertible subalgebra in E minus. So I constructed two maps for you. And if you restrict those maps onto these quotient groups, then it becomes isomorphs, inverse of each other. Give me a QCA, you look at, you consider the image of the half space, take out the non-trivial piece, and take that as a representative. Give me an instance of here. By using the decomposition of the bounded spread inverse, you construct a QCA that lands with here, and they are isomorphic.
So can you state again the corollary if we just talk about constant depth quantum circuits? What does it say about them?
Constant depth quantum circuit will be blending into identity, so it represents a trivial element here. And the trivial element here is now going to be just a usual matrix algebra, or
in
just
one dimension. In what dimension?
Any dimension. And in here, the trivial elements are represented by the tensor products. Because I always stabilize things.
So the non-trivial should be thought of as large depth circuits, or
Non-constant.
Non-constant. But
This probably, I guess the theorem one is just a super constant lower bound. Right?
actually, it turns out to be linear. Let me
Linear.
let me give you the reason. So
Linear in what? This is an infinite.
okay, let me get to that. Yeah. So suppose you had for the sake of simplicity, let me assume translation invariance in the sense that the image of this local operator and image of that is a translation of each other. If you give me such as translation invariant QCA, then on the infinite plane, then I can of course define this on a torus. Conversely, if you give me a QCA that is defined on the torus with the bounded spread, the parameter spread being much smaller than the radius of my torus, then I can unfurl this torus and promote it to a bounded spread isomorphism on the full infinite lattice. So absence of the bounded spread isomorphism on the infinite lattice, and if you knew that such isomorphism could be implemented, non-trivial instance of this in the infinite lattice, if you could define it on torus, then that means on a torus, if you were to implement that using circuit, the depth has to be grow big, so that the nominal light cone would touch the other end of the my torus. Otherwise, you could be unfurl and define and promote this non-trivial thing on the infinite lattice consistent quantum circuit. So that gives a lower bound on the circuit depth implementation by the linear size of my torus.
it's not square root.
Linear size, so like a d-dimensional torus is going to be dth root of the total number of sides.
What did you, I mean, somehow in the examples you started with, you use the codes and distance that parameterize the vector.
Yeah.
What is the analogy?
There's
some hidden distance in your particular algebra.
No.
So what is that?
The absence of a notion of distance is what this example makes it interesting. Everything looks completely local, yet they are not related by a trivial QCA. When you have a notion of codistance where you could apply, basically the notion of local algebra fails, and the axioms of network algebra, which are invariant under the bounded spread isomorphisms, that fails, then that immediately gives you a lower bound. But here we don't have, and we have to appeal to something else. And the notion I'm appealing to is the non-triviality of QCA in this sense. Okay, so.
And just one more question.
Yes.
You assume is the translation invariant for your argument.
Yeah.
But if you don't have the translation invariant, you cannot do this tools.
Well, there's an extra argument that you could basically reduce all the problems into the translation invariant case. It's called a torus trick, but I can tell you later if you want.
Okay.
Yeah. So the basic strategy here is that instead of proving some QC is non-trivial or not, I'm going to prove that invertible subalgebra associated with that is non-trivial. That's my strategy. And this is perhaps the physically most interesting piece. But let's take it for granted for the sake of time. And so for the step 2, because of this relation given by the 1, all I have to show is that fermionic invertible subalgebra in dimension 1 is trivial. then that implies the fermionic QC in dimension 2 is a quantum circuit plus shifts. And that implies that, well, the condition 3, that my final example is non-trivial. That's a bit of mouthful, but this is, yeah, as Sarah remarked earlier, this is the only step where the example becomes important. But maybe I will just focus on this because this is a new piece. This is an existing piece from some years ago.
Actually, do you want to explain what the bit in quotes in 3 means? Like,
it's exactly this. I was just copying this here.
oh, I see.
Yeah. This is from 2019 of one of my papers with Lukasz and Lukasz Witkowski and Matt Hastings. This is a paper from like 2 years ago from me, and this is an upcoming piece.
What is the dimension where that weird name group is non-trivial?
What?
What is dimension D where it becomes non-trivial?
Dimension D.
Yeah. So.
So right. So because of this new theorem, the Brouwer group in dimension 1 is 0, either fermionic or bosonic. So it becomes non-trivial in dimension 2. And indeed, that example is actually the only example we know for sure.
Is it all like related to Walker-1 model and 3-dimensional becomes like 2 dimensions?
Okay, so how do you show that invertible subalgebra in dimension 1 is trivial? So there is a very interesting, well, maybe very useful lemma, whose bosonic version appeared in the paper by Hastings and Mike Friedman, and it states the following. It's a completely finite dimensional algebra statement, has nothing to do with all those locality settings. Give me 2 algebras with a unital inclusion, both finite dimensional. So because of the Wedderburn theorem, each of them are direct sums of the full matrix algebra, repeated in some number of times. And I have an inclusion of 2 such things where the 1 is mapped onto 1 there, with a crucial. And so from the Wedderburn theorem, each isomorphism class of the algebra there's a canonical element associated directly from the algebra. There's projection onto the simple components. And that those projections, which are elements of this algebra by pi mu, these are canonical elements. And similarly, the Z will have a canonical projectors as well. The condition is.
So these are projections of the irreducible form.
That's the starting point. That's our assumption. Then when we get to this some picture, how does it look like?
So where this space you live, I mean, you multiply elements from the left and from the right are inside Z. You do it all inside.
This is a subalgebra. So you give me a unit inclusion of style algebras, and you look at the canonical projectors associated with the algebras. And if they factorize under the trace operation, by the way, trace is always defined for such a finite dimensional ones at least. And I inserted the trace of 1 just to avoid the normalization. I just want to forget about the normalization. So that the left and right hand are balanced. Then there is a middle central. So I call it as a simple between semi-simple. Simple between semi-simple. Just to give you a sense of where this is.
Maybe a naive question. What prevents you from doing this again?
Sorry?
What prevents you from doing this again?
You just wanted the central one.
I mean, why can't you have, I don't know, between X and Y another one?
Here, well, once you find the central one, then the central projector becomes just 1. There's nothing further you can do. So you may remember, so if you have 2 matrices, A tensor B, the trace of those 2 are product of the traces. It looks very similar to that. And essentially, we are going to use this lemma exactly for this reason. So it's like in the lattice setting, I have some algebra supported here, and say this is my X, and another algebra supported there. That's called Z. And I did not tell you, but for all invertible subalgebras, for those compact regions, all the central elements, especially the central canonical projectors, live on the boundary. This is where how U's are supported. Oh, I messed up the color. And this is the place where pi mu's are supported, which actually follows from one of the conditions for the net of algebras. The commutants of this thing should be should live outside the interior of this region, and this is just application of that. And since I have a clear separation between these 2 operators in support, I do have such a decomposition, and I have this. So basically, you give me a region in the invertible subalgebra, and then you consider some one algebra and then another one. And this lemma says, as long as the regions are finite, there exists something that sits in between that does not have any central element. It may look somewhat complicated, but there's an inductive step that you can reduce down to the situation where there are exactly 2 central projectors and 2 central projectors here. So how do you... So for each simple component, X will be embedded in some way. This is like the first component of C. And in another component of C, we will have, same algebra repeated some number of times. Because I assume there are only 2 things. So this is the fully general situation. And then because of this trace condition, the multiplicities should obey the same proportionality. You just read off the same blocks that are repeated and identify that as 1. Okay, so now how to the chain, in the new work we considered the graded version of this. The previous work was done only on the ungraded case. Excuse me. In the graded case, it turns out the same statement holds, except I have just that elements. I tensor in 1, the primitive graded algebra of dimension 2. Then, given X and Z with the unit inclusion obeying this condition, I find Y contained in, I should have written this here. I find the Y not exactly in Z, but slightly enlarged algebra. In fact, we have a counterexample. The lemma fails without this. Actually, it happens exactly in the 2-2 case. Yeah, so this stabilization is essential for this lemma to work. The next step. The next step is now it's the argument is special for the one dimension. So I am given a some invertible algebra in dimension 1, and I consider the set of elements contained in some interval. There are some elements here and there, but bounded by the support size A and B. And then I consider the center of this. And the lemma says the center actually factorizes. C left supported only on A, and Z right supported only around B. Moreover, the center has a characterization completely locally. So because of the net of algebra condition where whenever you see a central element, it has to be supported on the boundary of this region. The center of this interval algebra will be supported near here and there. The non-trivial piece is that there's no entanglement between the two ends. It actually factorizes in two pieces, and each piece does not know the other end. The center on the left is a commutant of any operator supported on this region that commutes with everything on a slightly larger region. Importantly, it does not refer to B at all. And similarly for the right-hand side. Now, using these two, now it becomes some geometric argument. Well, this lemma was crucial for the one dimension is crucial for this lemma to work. The next step is also crucial. I'll just do it here. So pick an element on the Z at the center. Okay, just a choice. And then
make sure where you're going. You're going to show that this invertible algebra is a product.
Yeah. So just to sketch the goal, what do we want? We want to decompose this invertible subalgebra as a product, a tensor product of localized central algebras. If we did that, then bounded isomorphism is trivial. Just map this central element, which is finite dimensional, down to some matrix algebra somewhere, and that suffices for our purpose. So the whole business is to find the central algebra that are mutually commuting, and such that they together generates the whole thing. That's the goal. So to that end, let me choose a projector on the left-hand side. And yeah, it's sitting somewhere here, it's 0. And then you consider the algebra times 0, K. So the central element of this thing was factorizing, and I project down to some one component on the left. So the central components of this projected one are always on the right. The left-hand side doesn't have any central elements. And then you consider, a nested set of algebras, nested pair of algebras, and apply this lemma. So central elements of the smaller one will be residing here. Central elements of the larger one will be residing there. Product of them will have a product trace because the support are different. And we find a central algebra that is supported like that. But this is ugly piece. This is unwanted piece. This is artificial component chosen out of this arbitrarily. So we want to forget about it. How do we do that? You consider so let's call this central element whose identity is pi, is not the original multiplicative unit in the original algebra, but pi, and labeled by k.
You're right.
And then you consider slightly larger one, and then think about the inclusion there. And you take a commutant of this within that, set of all elements here that commutes with all of that. Where can that be? That can be only somewhere here, multiplied by potentially by pi there. But pi is far away. So every representative in this commutant is a sum element here of A times pi, and you just read off this piece. And you generate an algebra out of those elements. And you can show that that is central. So that central algebra is now contained in this interval only, and you do it inductively for all intervals to the right. And you do the same thing for the all intervals to the left. There's some missing piece in the middle, but that missing piece is going to be the commutant of all the things that are constructed within the full algebra. And then now the construction is done. You now have to go ahead and show that this algebra indeed generates the full algebra. And we have successfully decomposed any invertibility algebra into the blocks of mutually commuting central ones. So the fermionic setting seemed quite different some years ago, but it turns out that using this stabilization is all we needed. But all the rest of the argument is kind of minor modification of the existing ones.
So should I think about this civilization physically as adding additional Majorana?
Yep. So indeed, the proper statement is that given fermionic invertible subalgebra in one dimension, you sprinkle one Majorana mode per site, and then apply this argument to find the central decomposition of the stabilized one, not the original one. And you show that.
Well, Majorana is not a physical degree, but you only have a single Majorana. How should I understand?
You got a lot in the lattice. You can always find a pair in the nearby location. So actually, if you don't like that, then just add in one complex fermion and then only use one Majorana. Okay, so let me just sketch how this works. So number 1 and 2 are sketched. Number 3 is most physical, and it's only relevant for the example. There are a lot that I didn't tell you about the example, except that it is an invertible example of invertible subalgebra. then one of the defining property of that is my example algebra contains some elements that are always local, and such that they all commute. And if you construct Hamiltonian out of it, then there is an emergent topological order. It's a synonymous to, for this purpose, just a toric code. Something like a toric code appears, except it's not toric code. Because the single term excitation interpreted as a particle is fermionic. Their self-statistics is different from that of the toric code. This is very physical word. I do not expect that everyone would understand what it means here, but it is something that physical, but at the same time, it's rigorizable. You can fully define what it means for these examples. In full generality, it's not an easy task, but for this example, it's not that difficult. And the emergent particles are here all fermions. And then you look at, now it comes to the calculation of the particular example. I don't want to mess up the calculation here, so let me add. What's the other way around? So one of the this is some element of my algebra that is going to be a term in my Hamiltonian, whose flipping represents a fermion. And now here we are going to map it down to some fermionic world. What do I mean by that? Take the commutant of this operator in the full algebra, not in A, but just full. The full algebra, the commutant of this operator and all the translates of this is spanned by so X, Y, and Z are all Pauli matrices that are 2 by 2. You can verify that this operator commutes with this one because there are, a pair of anti-commuting terms and so on. So the commutant of these terms in the full algebra is generated by these operators. It's just calculation. And then by going to the fermionic world, I mean the representation of these operators in terms of fermionic operators. So I assign two Majorana operators, the most primitive graded algebra, I call it Majorana. And I assign just two of them for every vertex in this grid. So originally the qubits are laid on the edges, but now Majoranas are on the vertices. And I represent and I associate these Majorana operator to those elements. And you can check that the commutation relation among the white operators is the same as commutation relation among the yellow operators. That's another piece of calculation you can do. So we effectively have a map from the commutant of this operator into the C2 graded algebra, consisting purely in terms of Majoranas, no other qubit figures. This map is not injective. Actually, the very operator that generated the commutant is mapped onto identity on the Majorana side. That's fine. And then you look at the Hamiltonian, which is, because of this condition, every Hamiltonian term is in the commutants of these operators. So you could write this operator in terms of Majoranas. You just do it.
Purely Majorana.
Yeah. Well, actually, there are qubit degrees of freedom that I didn't tell you about. So my example lives on the 2 to the 4. So 4 qubits per site. Or here, I only have 2 qubits per site. So there's a extra 2 qubits per site that I didn't draw here. Those degrees of freedom remain intact. So in my fermionic world, there are 2 Majorana modes per vertex, 1 qubit per edge. In the original system, there were 2 qubits per edge. So according to this map, you just map down to here. Now you do another piece of calculation to show that this Hamiltonian has no emergent non-trivial excitation. It's all, in some sense, trivial.
What does it mean?
It means that there exists, for every term you give me, there exists an operator that anti-commutes exactly with that operator and nothing else. So this is a piece of calculation you do. And now you assume, for the sake of contradiction, that A was trivial. But A was bounded spread isomorphic to its commutant. So the commutant must be bounded spread to the trivial tensor product algebra, in which you do have a trivial Hamiltonian. You write down the sum of all the sigma z terms, and every term there exists one operator that flips exactly one term. So the A has one Hamiltonian, and my hypothetically trivial commutant also has trivial Hamiltonian. Now, the full system has now 2 pieces, this trivial Hamiltonian and this piece. Altogether, they always belong to the commutants of this operator because A and B commuted. So any term here would commute with this by assumption of the being commutant. And then by calculation, any term here will commute with this. So you can define this map and you obtain some Hamiltonian. And then you calculate the particle content and show that there's nothing interesting. Every term is locally flippable and be done. And such a Hamiltonian always gives rise to the QCA, a fermionic line, because you just associate a term and its flipper to a local central algebra, and that defines an automorphism on the fermionic side. Now, at that point, you use the assumption that it is trivial. If it's trivial, then that automorphism must be consisting of a quantum circuit. And quantum circuit, you can look at individual gate, and individual gate is a some automorphism. And that has a pre-image under this mapping. So you could find another quantum circuit on the original system that will map this Hamiltonian down to something else. But trivial Hamiltonian on the Majorana side would contain this term. And translating into the original side, it will reproduce this product of z's. And we had another term that remained intact, and together it produces toric. And that's a contradiction.
Produces what?
It produces a Hamiltonian of toric code. Originally, we had the Hamiltonian that only had the emergent fermions, but now we have a Hamiltonian that also has an emergent boson. And the emergent particle being fermion or boson, they are regularizable concepts. So we obtain a genuine contradiction following from the assumption that the commutant of A, which was B, was trivial. Therefore, A should not be trivial, which in turn implies that QCA associated with this invertible subalgebra in dimension 2, the QCA in dimension 3, that cannot be blend equivalent to identity or shifts. And this algebra being non-trivial in this sense is not isomorphic to the tensor product algebra, and that gives us a lower bound on the isomorphism. Sorry, yeah, the last step is very rushed, yeah, this is the most example-dependent setting. Physical intuition is the following. Since we have an emergent fermion, you could represent its dynamics and its hopping operators purely in terms of the true physical Majoranians. And if you did that, then, in the original model, the fermions were transported by a string operator. But if you have a physical fermion, then you can create the fermion there. So you don't need a string operator anymore, and you're destroying the topological order. And indeed, that was the origin where I said this Hamiltonian was trivial. And if you could map that to the truly trivial Hamiltonian, that brings some finding of the toric code that has a boson inside. That is contradiction. Yeah. So let me just conclude with the one remark. If you read the operator algebra literature, especially in the context of mathematical physics, the discussion quickly runs into the subtleties of infinities and so on. But hardly this bounded isomorphism is at the center of the scene. But with this question, you can ask a lot finer classification of question. I'm saying this because this infinite tensor product is always isomorphic, if you ignore the underlying locality. It only depends on the local dimension, actually prime factorization of the local dimension. But with bounded isomorphism, there are a lot more possibilities. And this is one example, that is where that non-isomorphism is concretely established. Thanks for your attention.
Thanks very much. Any comments or questions?
So, since you're talking, I guess, okay, you showed a circuit lower ground on the operator algebra.
Yeah.
Now, let's say you take the torus and somehow construct a sort of ground space by pulling out commuting operators from your algebra. Is there a way to relate the circuit lower bound of the algebra to the circuit lower bound of states, which is the thing that people have mostly looked into in the past years?
The lower bound, okay, so first of all, there is no such thing as complexity for an algebra. You can bound a complexity for an isomorphism, but it's not a concept for the algebra itself. But I think you are referring to something like, what's the complexity to create, say, the toric code state on a sphere? It's a one-dimensional state, unique state. How come it is so different from the product state? You can ask about the unitary circuit complexity, starting with the product state and then resulting in the toric code state, and ask about the complexity. Here, similar thing is happening, except that you have it appears to be harder because you have to show, like, did I erase it? Yeah. Given an algebra itself may have some automorphism. And you want to show that this algebra is really different from that algebra. And this relationship always comes with the automorphism on both sides. Sure. So whatever you do on both sides, you have to show that this connection is hard.
But can't I just, I don't know, do the automorphism on one side and undo the isomorphism on the other side, U1 times U2 inverse, for example, if I think about, that is for quantum circuits.
Yeah. Yeah, it's not, there's no, I don't think there's any strict relationship between the two, the state complexity and the algebraic complexity.
Okay.
So, can you state the circuit complexity low bound for whatever? What is it for? To prove that any circuit converting including an isomorphism must be deep. What is the isomorphism? That's hard to do.
You mean the further use of this non-isomorphism?
I want the corollary of your theorem that is stated as a low bound on quantum circuits doing something.
That's related to the previous remark where we discussed the torus. So in this example, it's a translation invariance you could define on a torus of increasing sizes. Now, because of the Wedderburn theorem, that algebra is central, so it is isomorphic to the full operator algebra acting on some number of qubits. Now, it is isomorphic on a torus, so there exists a unitary. I could write that unitary in terms of quantum gates, and you ask about what's the complexity of that. Can you give a lower bound on the depth of that circuit? I said yes.
This low bound on the unitary that diagonalizes your algebra.
Yeah.
That's a very explicit.
Yes. Rather than random.
Right. So in terms of size n will be dynamic.
Yeah. So the specific lower bound is going to be like a linear in it's L by L, then it's omega L.
Yeah. And this, at the end, I didn't understand this physics part, but you generate a boson from fermions, but it seemed to be a code, right? I mean, so you found an element of the toric code.
Yes.
Which has distance.
Yes.
This distance is not explicitly or implicitly used in the steps of
No, not used. Even in this example, you can think about you can argue that this is a code, and if you interpret it as a code because it has the Bijet ground states and satisfy almost all properties, then its codistance is also L. The same on both sides. So distance alone does not give you anything.
Yeah, because it's start also from that. How it is.
Yeah.
Any more questions or comments? All right, thanks. More?
Sorry, one more question on your last comment.
Yes.
So you said at the end, if you look at the infinite value as a sister algebra, these are just isomorphic for A.
I would guess so, but I'm not totally sure. As an abstract sister algebra, I would guess they're isomorphic. Yes. Okay. But I'm not totally sure.
Okay, let's take everything else off.